Today we have Zinan Lin from Microsoft Research. He's going to be telling us about differentially private synthetic data without training, which is a topic that I know many of us are interested in.
Yeah, thanks for the introduction. And yeah, it's a great honor to have the chance to talk here at Google. Yeah, my name is Zinan Lin. So I'm a researcher at Microsoft Research, working on generative modeling and privacy. So today I'm going to talk about our work on differentially private synthetic data without training. It is a joint work with my amazing colleagues and interns. So we all know that oh, by the way, if there's anything unclear, feel free to stop me in the middle. Yeah, so we know that currently data is very important in the current big data era. For example, from the data, we can do a lot of applications like training foundation models, sharing the data across different organizations or between between companies and academia for collaboration, and also for debugging why the system or why a product doesn't work or not. The data scientist needs to look at the data directly in order to figure out the problems. But at the same time, we know that a lot of the data, especially the high quality data, actually coming from the end users. So they contain a lot of sensitive information about individual users, like medical records or code or email, etc. So because of the privacy concerns, we should be really careful about how we use the data. Firstly, there's a lot of data regulations like GDPR, etc. that restricts us to protect the privacy of the data. And also technically, we all know that, for example, if we use the data to train a machine learning model, the machine learning model might just memorize the training data, which will lead to a lot of privacy concerns. So how to deal with, how should we, at the same time, utilize the data while protecting the privacy of the sensitive information in the data? So something called a differentially private synthetic data is something have been started in the community for a long time for addressing this issue. So what do I mean by differentially private synthetic data? So here, let's say the original data are some human face images. Then this differentially private synthetic data, firstly, must be a synthetic data fake. You can think of it as a fake data, look very similar to the original data. So in this case, it's also some images about human faces. But at the same time, we need to have a strict privacy guarantee called the differential privacy. So I will detail what this means in the next slide. But here you can think of it as a high level that this differential privacy is a strict privacy guarantee on the leakage of the information from the private data. Okay, and then at the same time, this differential privacy has a very nice property called the post-processing property. So which means that we can do any post-processing on this differentially private synthetic data in any way we want, and we still have the same privacy guarantee. Okay. So this means that we can use this differentially private synthetic data in replacement of the original sensitive user data in any applications, training machine learning models or looking at it or sharing with other organizations without worrying about the privacy. Okay. Yeah. So here I talk about differential privacy. So what exactly this means? So this differential privacy is the privacy notion created by things that they work at all in 2006. She was at MSI at that time, and this is also adopted by US government and several companies in industry. So what it means is that we say an algorithm or any data processing pipeline is differentially private if, let's say, we give it two data sets, they only differ one sample, okay? And depending on what the algorithm is, it will produce some output, for example, if a machine learning training algorithm could produce a machine learning model, or it could produce some data sets, or it could produce some results, summary statistics of the data set. It could be anything. In this case, it's going in our context, it's a differentially private synthetic data set. Okay, so given these two data sets only differ two samples, like separately, we put them into this algorithm. It's going to produce two sets of output, and this algorithm is called is differentially private. If for an attacker that sees the output, he cannot tell like whether the original input data set was data 1 or data 2. Okay, so it's high level what this differentially privacy means. Yeah, for the sake of time, I'm going to skip the mathematical details, but the only thing I will like need to use later is that like for DP algorithm, we will typically use two numbers, epsilon delta, to characterize like its privacy level. So smaller epsilon delta, it means better privacy. Okay, so this is a very high level introduction of differential privacy. And as mentioned, like differentially private synthetic data is one like popular approach to address the privacy issue. So how do we generate this differentially private synthetic data? So the most popular or the widely used algorithm in the past few years is something called DP fine-tuning. Okay, so what I mean is this: so we will take a pre-trained model, pre-trained generative models. Like for text, you can take like GPT or like GPT-2 or like Llama. For images, we can take Stable Diffusion or something like that. And then we will use it to like use private data to DP fine-tune it. Okay, so here what I mean by DP fine-tune. So it's like our in the non-DP world, like all people are doing like this fine-tuning. But here the only difference is that we will use a special algorithm called the DPSGD that will guarantee the differential privacy. Okay. So we will use private data set and use DPSGD to fine-tune the model, and we're going to get a fine-tuned model that is knows more information about the private data. And because it's a generative model, so we can use it to generate the synthetic data set. And because of the post-processing property, like this data set is going to be differentially private. So it is the differentially private synthetic data that we want. Okay. So this approach is kind of the dominant approach in the past few years. But what we realize is that we think this algorithm is no longer fits in the current large model paradigm. So why is this? So let's consider this algorithm, right? So I mentioned here, like we need to take a pre-trained generative model. So the question is, what model should we use? Okay. So what people found in the prior research is that, like, if this pre-trained model is stronger, it has seen more data during a pre-training stage, then the DP synthetic data is going to have a high quality, which is makes a lot of sense. So and we know that the most powerful pre-trained model are usually closed sourced, right? Like ChatGPT or Gemini or DALL-E 3, etc. They are all like behind the API, so we don't have the weight access. So now the immediate problem is that because those models only provides inference, so we cannot we don't have the weight access. So like as a client, that we cannot basically do DP fine-tuning on it. So you may say that like for example like ChatGPT, some OpenAI model, they provide this fine-tuning API. But one thing to note is that like here we need a special fine-tuning algorithm, like as I mentioned, DPSGD. So it is different from the traditional non-private SGD optimization. So it needs a special implementation, and currently those models do not provide such DP fine-tuning API, so we can not utilize them at all. Okay. So now moving one step further, like you may wonder, what if like in the future, like Google or OpenAI, I mean, they provide this DP fine-tuning API to people, then is this problem solved? Like in my opinion, it is still not, because those models and APIs are hosted by third-party company. So it is very scary. Like if like let's say I'm a small company, I have some data, I want to generate a DP fine-tuning, DP synthetic data set. You require me to upload my sensitive data to a third party and then let them to DP fine-tune it for you. It sounds very scary, and also like maybe some like regulation will avoid, like will don't allow us to do that. So in most cases, because those data are very sensitive, so clients or customers usually want to keep them local. So even if those company provide this API, maybe it's still not workable. So now the only option left is that we can use open source models. Then the immediate problem is that most of the open source model, like they have worse quality than the most successful foundation model black box like API behind the API models. So the quality, since DB synthetic data quality might be worse. And secondly, like the computation cost and the implementation cost is going to be high. Yeah, because like we know that because those models are very large, like even for the traditional like non-private fine-tuning is already requires a lot of like GPU memory and computation. And this DPHD requires even higher computation because it needs to compute simple gradients. So the computation cost is going to be even larger. And also like in implementation is not like straightforward. Yeah, so this is like why we think like this DP fine-tuning, although it's the dominant approach in the past few years, we think we really need a different algorithm so that it like aligns with the trend in this machine learning world better. And in last year, we proposed this new framework called the private evolution to address this issue. So firstly, this private evolution only requires inference APIs to the model, so it does not need any training. So this means that this approach can utilize any like either API-based models or open source models. Okay, and secondly, like we can keep the data. We never upload the original private data to the API. So the whatever model we use, they will not directly touch the private data. So it's also better in terms of this privacy, the second point. And what's surprising is that even though we do not do any training, we see that in some cases, like our DP synthetic data quality might be like match or sometimes even outperform the training-based approaches. So also has good quality. And also like because we only need inference, so the computation cost is going to be smaller. And this private evolution is based on these 3 papers from us. But since we published the paper, there are actually many there are actually more interesting paper coming from the community than from us. So here, like in this link, you can see like the full list of the private evolution papers from the community. And we also open source their like Python library for people to easily use or build on private evolution. And since till today, like private evolution has been adopted by Microsoft and Apple. So this is like a brief high-level overview of private evolution. And before I dive into like more details about like these algorithms results, is there any questions so far? Okay. Okay. Yeah. Yeah. If you have, feel free to interrupt me anytime. Yeah. So now let's look at like how this private evolution works. So let me first introduce like what is workflow. So let's say like the data holder will have the private data, and the private evolution will take this private data as input, and then it will send some API queries to the foundation models, and then generate the DP synthetic data. Okay, and the one thing to note is that, sorry, excuse me. One thing to note is that like this API provider can be untrusted, like because all the API queries we send to the foundation model also have the differential privacy guarantee. Okay, so we want to send like a private data directly to the API provider. So I think this is something very important for the adoption of this framework, because like not every company like or clients who wants to generate DP synthetic data, they have the computation power to host their own model, or like many of them are not Google or Microsoft, so they do not have their own like large language models. So they need to like use some like API provider from other companies, and this probably is something very important, so that they might be more willing to utilize this framework to generate DP synthetic data. Okay. Yeah, and here I mentioned that like this private evolution will need to send some API queries to the foundation model. So what are the API queries? So currently we use like 2 APIs. So one is random API. So what I mean is that we will ask the foundation model to generate some random samples, And the other is a variation API, which means that we will give the foundation model one sample and ask it to generate something similar. Okay, so this might be a little bit abstract. So let me give you concrete examples. Let's say like we want to generate some images. Okay, so for random API, we just call the foundation model to generate some random images. So it's like if you go to imaging or like a stable diffusion or DALL-E, you can just put a random prompt to the model and they can generate some random images for you. Okay, and the second is the variation API, which means that we just give the model one image and then ask it to generate something similar. So like for example, give it a bird image and it's going to generate something like some variation of the bird. And this is also like provided by many off-the-shelf models like Stable Diffusion or DALL-E 2. Yeah, so these APIs are pretty general, okay? And this is for images. And then what about text? Okay, so at the first glance, like you may wonder, like a text, like the only thing like the model provides is a chat interface, right? So you can chat with the model. So they do not have this such a random API and variation API provided. But actually, like because of the instruction following capability of those models, it's actually more flexible to implement these two. So let's say we want to generate some restaurant reviews. So restaurant reviews are the private data set. For random API, we can just use prompting to tell the model, write a random review for restaurants. Okay, right. So you can generate a random review for us. And what about variation API? Like again, we can just use prompting, right? So we can say, please rephrase the review and then put this review as input, append to the prompt, and then the model is going to generate the variation for us. So it is actually like very straightforward and very easy. Yeah, so these two are the only APIs we need. So the next question is how Private Diffusion is able to generate DP synthetic data purely just based on these two APIs. So firstly, let me give you some high-level idea like of how Private Diffusion works. So we know that foundation models, they are pre-trained on a lot of data, so they have a very great world knowledge about everything in the world. So if we visualize their distribution, it's going to be like very flat, like very broad, have a very broad support. And the private data set might be something like a very spiky in the middle. So this means that like if we just like call the foundation model to generate some random sample, basically the random API is going to generate something like have a very large distance to the private data. So it is not what we want. But then what we can do is that we can use the private samples to select the samples that are close to the private data. And then it becomes the next set of our samples. And then like because doing like the hope is that like some of these random samples we get from the random API, some might be closer to the private data, some might be further away. So we want to select the ones that are closer to the private data. But they might be limited in quantity. So what we do next is that we call the variation API to generate something similar to augment their quantity, and then that becomes the next population. And then you can imagine that this sample is going to be closer to the private data because we did a selection. And the algorithm will work towards this loop iteratively so that the synthetic data set will be closer and closer to the private data set through iterations. Okay. So this might be still a little bit abstract. So let me give you concrete examples. So let's say the private data set is images. There are some bird images. I mean, for other data modality like text, it works in the same way, but I just use images for better visualization. Okay. So the first step, we're going to call the foundation model like Stable Diffusion or DALL-E. We just ask it to generate some random images. Okay. It's going to be generating some like planes or cars, which is nothing related to birds. But maybe let's say like assume this time we happen to get a bird image, but all others are very different. Okay, and then the next step for each private sample, we are going to let them to find which generated sample is the most similar. Okay, so all of them is going to pick this bird image. And then for each synthetic images, we're going to count like how many private images have been voted for them. Like so this bird image will get 3 and the other images will get 0. So you see that now we get some information from the private data. We know that this bird image is closer to the private data sets, which is great. But because this step, like we touch the private data set, so we need to do something to ensure the differential privacy guarantee. So here I'm going to skip the mathematical details, but on a high level, like because each private sample only provide very limited information, just one, like 0, 1 towards those samples. So we can prove that we can simply add some Gaussian noise to those counts, and we're going to have the strict privacy guarantee. Okay. And now we got this new noisy count. The next step is going to we're going to redraw those synthetic samples proportional to their noisy counts, so that the spurt image, which is closer to the private data set, has a more likelihood to be retained, and the other samples are more likely to be dropped. So let's assume here that we got lucky and only the spurt image is left. Okay. And then we're going to call the variation API to ask the model to generate more similar images. So it's going, because the foundation model is trained on a lot of data, so it's a very good word knowledge. If you give the bird image, it's going to generate some more bird images for you. So you can see these 3 images, the bird images apparently is closer to the private data set than the initial data set, which has cars and other things. And this is the end of the first iteration. So what we are going to do next is that we will use these synthetic samples as the initialization for the next iteration. So I'm going to again do this private data set, private sample selection, and resampling, and then call variation API to iteratively move these private samples towards the synthetic sample towards the private samples. Yeah. So this is kind of the idea of the algorithm. And here, I'm giving you a very simplified example where in the initialization we happen to get a very good bird image. In reality, it's going to be more challenging than this. So how does private diffusion work? So here I'm give you several visualizations. So these are real example run by LP algorithm. So here the private data set is something called the Camelon data set. So it's some just images of breast cancer cells. So it looks like this. And then here we are taking a pre-trained model, pre-trained on ImageNet data set. So if you know this ImageNet data set contains photos of real world objects. So apparently it looks very different from those cell images. And if we run this private diffusion algorithm through many iterations, we see that at iteration 3, it starts getting the color similar to the private data sets, but the pattern is still quite different. And then if we run it for more iteration at iteration 21st, then we see the pattern is also look very similar to the private data set, which is quite amazing. And this is an example on images. So and here is another example on text. So here we are using some paper reviews, treat some paper reviews as the private data set. And the ground truth sample is something about adversarial detection, etc. And at iteration 0 just means we randomly draw samples from the pre-trained model. Apparently it's talking about something unrelated like privacy, etc. And through many p iterations, then we see the sample starts getting closer to the private data, it's talking about something adversarial text, etc. So for text, it can also shift the distribution towards the private data set. Yeah. Okay. Oh, so I see a question. Hands up.
Yeah, I have a question. Maybe you will cover this in the next bullet point, but I was wondering, do you have any formal privacy guarantees in terms of, is it something that you're gonna cover next?
Oh, so I didn't put it in the slide, but yeah, it does have the strict privacy differential privacy guarantee. So it has the same differential privacy guarantee as the DP fine-tuning, in the sense that we protect the samples, private labels, etc.
But do you need to assume anything about the large language model you're querying?
No. We do not need to have any assumption on that. So I mean, we need assumption that the pre-trained model, the pre-trained data set has no overlap with the private data set. But this is the kind of the same assumption as DP fine-tuning. Like if we take the pre-trained model, like we do DP fine-tuning. So basically the privacy guarantee is only protected against the private data sets that you feed into. Like, so we do not consider potential issue
So
about
you don't have to make any assumptions whatsoever about this notion of similarity that you are relying upon.
No, yeah. So the high level idea, like why we can protect the privacy, is that like the only step in the whole algorithm that touches the private data is this step. Like each private sample will select the closed sample, and so you can think of like each private sample will contribute a vector. In this case, it's a one-hot vector, but I mean, like for the follow-up work, we can extend it to more complicated case. But here, like it's just a one-hot vector. Like for example, this bird image is going to contribute a vector like 0, 1, 0. So this vector has a bounded L2 norm, right? So the L2 norm is just 1.
I see.
Yeah, so we can use standard Gaussian mechanism to give the privacy guarantee. I see another question.
Yeah, did you experiment with different budget splitting schemes? Like, is it best to like split the budget evenly among iterations or to increase the budget? Like, what's your intuition also for like number of iterations? Like, I don't know, just curious if you have rules of thumb.
Yeah. That's a great question. So currently, like in all our experiments, we just play with the simplest scheme where the privacy budget is uniform across all iterations. So we add the same amount of noise across all iteration. But indeed, like this is something like may have some space for improvement, because like what we see in the experiments is that usually in the first iteration, this health histogram is going to be very very sharp. Like all the histogram counts are concentrated on very few examples, because initially, like most of the sample are pretty random. Only a few is closer to the private data set. So in this case, we can actually bear to add more noise. But in the later iteration, as the data set becomes closer and closer to the private data set, this histogram is going to be very flat. In this case, like if we still add a same amount of noise, like the signal is going to be like buried by the noise. So maybe we can spend like more privacy cost. Yeah. So indeed, like from what we observe, I guess that like it could improve the performance. But yeah, we didn't try that yet. But yeah, that's a great idea.
I remember, did you say that after adding noise, you subsample based on the weight? Is the subsampling for privacy reason or just getting some randomness?
It's actually not necessary and not optimal. So here I'm just saying the most simple version, like which we propose in the first PE paper. We do subsampling. But this is actually not optimal. So in the second like a paper of P, like P for text, we actually do something like take the top K samples with top K votes. And internally, we have done some more experiments that we didn't write it in a paper. But I mean, like this is a step that has a lot of space for improvement. So this subsampling is just something, I mean, intuitively makes sense, because like we want to capture the distribution of the private samples. So we want to like draw samples proportional to like basically gives the same weight as to all private samples. Like if like there are 3 samples voted for this bird image, then we want to sample like this image 3 times because it represents 3 images. So it is kind of like the hell of idea. But because this subsampling introduced some randomness, so it's actually increase the variance of the algorithm and hurts performance. So this is not necessarily the best option. So like taking the top K or something more advanced, like might be better.
Oh, yeah. Thanks.
So we have mentioned like how this private division algorithm works, and then let's look at some more concrete results. So this figure is the results on images. I mean, there are many lines, so it looks scary, but I will explain them like one by one. So here the y-axis is the FID, which is popular metric for image quality, so lower is better. And then x-axis is the x-axis is the privacy. So I mentioned this epsilon. So epsilon smaller means better privacy. Okay. So and each line here is one method. So especially like this yellow line is the previous SoTA algorithm based on DP fine-tuning from Google into 2023. And this red line is our private evolution algorithm. So you can see that we'll achieve much better privacy utility trade-off than this DP fine-tuning approach. Like for example, if we want to achieve a FID score at 8, then this previous SoTA requires epsilon equals to 32, but we require only maybe 0.8 or 0.7 something like that. And if you're familiar with DP, this epsilon is actually in the explosional scale, but even on that we improve quite a lot. So it's actually a huge privacy saving. And then this is results on text. Okay, so here again, we compare with the previous DP fine-tuning SoTA. So this method achieved got the honorable mention award in ACL 2023. So here the metrics is that we train a synthetic data set on some downstream task, classification task, and then evaluate its accuracy. So the previous SoTA achieved 32 accuracy, and our method achieved 37. And one thing important to note is that here we are testing both methods based on the same pre-trained model, just GPT-2. But as I mentioned, the benefit of private evolution is that it can utilize more models very easily because we do not need to do any fine-tuning. So it's very easy in terms of implementation and the computation cost. So this table is basically extend the previous table, but we add apply private evolution on more open source models. So some of them are very hard to fine-tune because the implementation challenges and GPU memory requirements. Also, for this GPT 3.5, because it's behind the API, so it's actually impossible for DP fine-tuning method to work. And what we see is that a private evolution with more advanced models can apparently achieve even better classification accuracy. Okay, so this is on the performance side, and then the next slide is about the computation cost. So for text and images, what we see is that we can this is evaluated based on open source model, so we can fairly evaluate the computation cost of DP fine-tuning and our method based on GPU hours. So for both text and images, we can achieve a considerable speed up because we only need to do inference, no training at all. Yeah, so all is about some positive results about private evolution, but also want to mention some negative results or some limitations of private evolution. So what we found is that private evolution will perform much worse than DP fine-tuning when there's a large distribution shift. So what I mean is that if the private data set is very different from the pre-training data set. So here I'm showing an example on MNIST data set. So it's a very old but popular data set, so with some images of handwritten digits. And the SoTA DP fine-tuning method can generate something like this, which looks pretty reasonable. All the digits are recognizable. And if we train a downstream digit classification algorithm, it has a quite good accuracy, 97%. However, if we run it on our private evolution using a pre-trained model trained on this ImageNet, basically something we have seen some nature photos, then the private evolution is going to generate something like this. So it's not for maybe 0 is good, but for 1 is good, but for many other digits, it's not recognizable what the digits is. And if we train the downstream classification accuracy, it's very bad. It only has 32.7 accuracy. So I'm going to sorry, go ahead.
Yeah, I just had a question about the last result. So if I understand correctly, private evolution can only output examples that are oh wait, never mind. I'm all good. Yeah.
Okay, good. Thanks. Yeah. So yeah. So here, the reason for this bad performance is also understandable. Because for DP fine-tuning, they are able to change the parameter of the foundation model, so it's more easily for the model to shift its generated distribution. But for private evolution, we do not do any training, so it's purely based on a generated sample from the foundation model. I mean, the private data will guide the generation towards the region that are closer, but still, we do not change the parameter, so it's harder for the model to dramatically change the generative distribution in a very fast way. But I'm going to talk about like how potentially we can address this issue later. But this is something I want to highlight. Like there are also some settings where currently still worse than DP fine-tuning. Okay. Good. Yeah. So we have talked about the results. And then like next I'm going to talk about some like extensions of private evolution. So as I mentioned, like some of the extensions are coming from us, but more of the extensions are coming from the community. There are many like interesting paper coming from the community. So I'm going to talk about like some of them. But if you are interested, you can go to this link, which has a full list of the private evolution papers. Okay. So the first thing is like a paper coming from this year. I think it appears in ISML of leveraging multiple foundation models. So the idea, I mean, this paper has many interesting ideas. So I'm only mentioning one of it. So apparently, like we know, like different foundation models have very different strengths. This is something that in the non-private world, like people explore a lot, like maybe some model good at math, some model good at English, like we combine them together to get a very models good at both. But for like the privacy, like a DP synthetic data generation, currently, like if we based on DP fine-tuning, it's very hard to make it happen. But for private evolution, it's very easy because private evolution only requires the API access to the foundation models, right? And all those models provide the same API to us, for example, like chat interface or image generation. So we can actually very easy to utilize all the models together, like by switching like different models at different variation API or render API calls, right? And this, as I mentioned, this is something might be hard for DP fine-tuning. As firstly, like a DP fine-tuning usually requires separate implementation for different code base. Like if you have tried to implement DPHD, you will realize that. And also like if you train like multiple models, then you're going to have like actual privacy cost. But for private evolution, like if we want to utilize multiple models, it's very easy in terms of the implementation and the friendly about the privacy cost. And what I found in the paper is that like, for example, if we, this OCP is our private evolution algorithm. So if we do private evolution on a single model, we get these results. How is better. But if we use their approach, we're going to, utilizing all the model together, we're going to get better results across data sets. Okay, so now like one thing you might wonder, you might ask is like, what if we just take the strongest model that has the strongest capability across all fields? In that case, do we like simply use one model is sufficient? And they also have very, very interesting results. Like they try this our private evolution on 3 models, and they are frontier models. Like for instance, GPT-4, they all have very good performance. But they still see like if you utilize all of them, then we will get even better results, which actually makes sense. Like because it's really hard to imagine like there's one model that dominates all other models in all fields. Like maybe in general it's better, but there might be still some fields or maybe some bias. Like other small models, although they have worse quality, and they might have smaller bias, or maybe they exceeds like the best model in some small domains. So in this case, there's still a benefit of utilizing multiple models together, which is interesting. Yeah. Okay. And this is one work. And then like if we move one step further, like all the previous things I talked about is utilizing foundation models, right? And also like it's also the same for the DP fine-tuning, right? DP fine-tuning is using neural network like machine learning models to generate DP synthetic data. But one observation we see is that actually even till today, with like a lot of good foundation models, there are still many domains where foundation models are either not available or its quality is worse than the traditional non-neural network data science tools. Like for example, for networking domain, like the best approach, like in terms of data quality, is still based on like some simulators, Like we still don't have a very good foundation model for generating, like for example, networking packets till today. And also like for images and videos, like the domain where foundation model is very successful, there are still many applications that people still utilize computer graphics-based renderer. Like for example, for movie generation, for cartoon generation, like people still use like Unreal or some other those computer graphics-based renderers. Now the interesting question is that actually private evolution can also utilize them very easily, right? Because all the thing private evolution requires is a render API and the variation API, and they do not have to come from foundation models. They can also come from the simulators or other non-neural network tools. So this is what we explore like in this paper. So it has two implications. One is that it can greatly expand the capability of private evolution, which I will mention in the next slide. But also like for the DP synthetic data generation, like in the past, the community heavily rely on foundation models and didn't utilize the power of those non-neural network data synthesis tools. But private evolution provides one way to introduce their capability into this field. And here is one example. Like again, this is the results you see. Like on MNIST, we have very poor. If we use private evolution with foundation model, we have very poor data quality. But like if we use a non-neural network data synthesis tool, we can generate something like this, which is much higher quality. And we got to also like improve the downstream classification accuracy quite a lot. Okay. Yeah, so this is one work. And then if we move further, one step further, like all the previous approach I mentioned, like are just applying private evolution for DP synthetic data generation. But interestingly, like there's people from the community has very interesting work that actually apply private evolution for other domains to improve other domains as well. So this paper by Ho et al. From Meta and Simu has this very nice work. So for federated learning, if you're familiar, like it's considered a different setting, like where there's a central server that has a model and they want to train the model, but the data is on the client side, like for example, like phones or like computers. Those clients, they control the data, and the model, the central server wants to train a model collectively using the data from the client. And the federated learning typically will do this training distributedly, like they will send the current model to the client. The model will update the model based on its own data, multiple iterations, and send the model updates back to the central server. And central server will aggregate those updates that becomes the next model, and do this iteratively. And this approach is going to have an expensive client training. Like not all like a client device has the capability to train model, especially if the model is very large, so which is not good. And also it has a high communication cost because we need to send the model back and forth if the model is very large. And the approach they propose is this. So they will use the central foundation model to first generate some synthetic data, and then they only send the synthetic data to the client. And the client will use the private evolution to use its own private data to vote for the good synthetic data that can represent its own data, and then send the votes back to the central server, and the central server can utilize the votes to select the synthetic data that is the best, and then they can fine-tune the client, fine-tune the model based on the synthetic data. Yeah, so it's a new different way to do this federated learning. It has a cheaper client communication and cheaper communication. And I believe the same author also recently has also another further more work on it, that basically further advanced this framework where they used this private evolution votes as the rewards in the reinforcement learning pipeline to fine-tune the model, which is yeah, even more interesting. Yeah, so this is kind of like a quick overview for like 3 follow-up work, but again, like there are many more interesting work, so you can go to this link. So now let me summarize this talk. So we mentioned this private evolution, where the goal is to unlock both the value and the privacy of the user data, and we propose this framework that requires no training, no access to the weights are needed, and only requires the inference APIs of the model. So it is compatible with both open source model and API-based model, and also like other data synthesis tools that is not based on neural network. And this is computationally cheap because we do not do training. Works for both images and text, and we are currently also like further expanding its data modality. And they can bench or even outperform DB fine-tuning in some cases in terms of the data quality and the privacy trade-off. Yeah, so this is the end of the talk. And yeah, if you have any further questions, like, yeah, I'm happy to discuss it further. Thank you.